Hi everyone, welcome back to this channel. In this video I'm going to show you the difference between the calibrations method that's available in FieldFox. So today we have a N9918B in front of us, as you can see here, and this is my connections. So I have a 3.5mm cable, so this is a male, this is a female. So my device under test is a 20 dB attenuator. And you can see that there is eCal here, is N7555 series, so that goes up to 26.5, which is the same frequency range for this N9918 series. So as you can see here, on the right side is the screen on FieldFox. Let me enlarge it a bit. What I'm going to show you is the difference result when you use normalizations and also eCal. So we're going to put in the data to memory and then compare before and after the calibrations. So you can see how much deviations it has from each calibration. So let's go back to the default. So network analyzer, mode network analyzer. So on top of this is a log magnitude, down here is a phase. So I'm going to preset it so that you can see how I'm setting it up. After preset, we set to S21 measurements. There's nothing there because it's not connected. There's nothing to measure in between the ports. The next thing we want to do is to set this frequency range because we don't really want to waste too much time in scanning to 26.5 gig. Let's start with 1 gigahertz and then we stop at 5 gigahertz. The next thing I want to change is the resolutions. So 1 gig to 5 gig is about 4 gig of bandwidth, so let's set it to 1001 points. It should give you a good reading. You can really see that. Let's connect it together so that you can see what's going on. So for the benefit of this video, what I'm going to do is to change the resolution bandwidth so that we can hit the noise floor, let's say to 1 kilohertz. So as you can see right now, the scanning is a bit slower. The sweep time is 1.83 seconds per sweep. And we have a delta, a loss of 1.08 dB, which is from the top of the FieldFox to port 1 to port 2. So it's contributed by this cable. So as you can see, this is direct connection, so assuming that this 1 dB is from this cable. So the next thing I want to do, I already done changing the points and also I have bandwidth. The next thing I want to do, I return on the marker. I want to turn down the power. The reason being is that at high power you can't really see the deviations. So I'll push it down to further -30. You can't see anything change here because the power level is still alright for just a go through and 1 dB attenuation. So the next thing I want to do is to add on another trace for phase. So I go to trace and then I have 2. And then I change this, the bottom one. As you can see, it's highlighted in the hint of green here. I want to change that to phase measurements. Go to format, phase. So as you can see, it is before calibrations and I get all the funny reading here. Right, let's put in the attenuator and do a rough measurements first and see is that what we want and see whether our power is sufficient to make a difference for the measurements. So just leave it there. That is a 20 dB attenuator. So as you can see, roughly about -21.13 dB at 3 gig. 1 dB is contributed by the cable and the phase is still haywire. Right, the next thing I want to show you is this. Let's go to Cal, and the first thing I want to do is do a response Cal normalizations because we are using 2 ports. We want to get rid of the effects from the cable that's connected to this device under test. So let's do a normalizations. So in layman term, normalizations is getting the fundamental, the baseline of the instruments of your setup, including the jumper cable. So let's do a normalizations. It might take a while. Once you're done, and we just click finish. So as you can see, without changing anything here, we should get a 0 dB. Makes sense because it's normalized and it's also normalized in the phase measurements. So let's put back the device on the test, which is the attenuator. So this is a reading and it makes sense. It's about -20 dB loss, and this is the phase property. Let's put that into memory. Let's go to trace, math and memory, data to memory, and data to memory. So what I did is just for the phase, so I need to click escape and move that green box up, and I'll do the same thing, data to memory and data and memory. So I want to show you the calibration is there, so let's turn it off and escape. So you can see that before and after there's some difference here. So let's go to the magnitude, let's turn the scale down and reference level somewhere about 20 here. So the top line is after cal, the bottom line is before cal, same as this phase. So let's turn back on the calibrations. So just bear in mind, this is a normalization. You can view cal, what they have done. So normalize true response. So it's back to the same measurement. Right, so the next thing I want to do is to use the ecal to do the calibrations. So I wanted to use the mechanical cal, but unfortunately I'm not able to find it in my stash. So the next best thing is this ecal. So I just leave it like that. So as you can see, it's connected, and this is how it looks like. Let's do the calibrations. So for ecal, there are a few choices that you can select. I'm going to show you now. So I won't go through change that connector because it's already done, and I have this cal kit here ready. So currently it says a forward enhanced response recommended, but we do not want to try that. We want to try SOLT, short open load true, known and unknown true. But if you want to see it, I can show you. Change that connector. And also this is where you're going to select the type of cal kit that you're going to use. So mine is the first one. So remember the dot at port 1. So it's the opposite of your cable. And then next. So this is where you can select the type of calibrations kit over here. So I'm using the ecal, so I just use that. Then I change the cal type. So the first one I want to try is full 2 parts. Short open load, not sure the R stand for, but it's unknown true. Select, and let's start calibrations. We just follow the step, connect ecal between port 1 and port 2. So once you click finish, so this is the output of the ecal. Well, you might ask, if the last step for the calibration is a true, why am I seeing a -4.4 dB on the ecal? I did talk to the product expert for this ecal and say it is what it is. This is how ecal works. In detail, if you need more information, talk to your local support for Keysight. Ask them about these questions. They probably give you a better answer than what I'm trying to give you right now. So anyway, anyhow, the calibration is done on ecal. Let's connect back the attenuator. I know you're going to say that I'm not using a torque wrench to tighten when the calibrations, but again, this is just a proof of concept to show you the difference between different type of calibrations. If you want to, you can give it a try with a torque wrench. Right, so what we are seeing here right now, so the scale is still quite huge. You can't really see the difference. So I will lessen down the scale and change the positions without changing the attenuations. So as you can see, it's quite on top of each other. It's about 0.1 dB difference. So this is with the unknown true. And let's change the screen on the face and then change the scale. So as you can see, even for the face, it's pretty much on top of each other. So let's check back, calibration. Let me turn off the cal. You'll just mess up. It'll be like before calibrations. Let's turn back on the cal and view cal. So this is what I've done. It's a full 2-port ecal. This unknown true cal. So this again, this is how it looks like. And we have the memory data as the normalizations. So it's pretty much on top of each other. So the next one I want to do is the ecal with a known true. If you want to know more about unknown and known true, I think the best way is to talk to a AI machine, Copilot, ChatGPT. They're able to explain to you much more detail. Let's go to mechanical and change the cal type and SOLT. I'm going to show you the QSOLT later. So right now it's a known true SOLT. Before that, we need to change the connections to ecal. Alright, so this time I'm going to use the top wrench to tighten it. So connect ecal between port 1 and port 2. Same thing. Then click finish and you're done for ecal known true calibrations. So again, the loss is about minus 4.4. We're seeing the same thing. So the trace is also on top of each other, maybe a 0.1 dB difference. And as you can see, the calibrations for all three normalizations, then full 2 ports with unknown true and also full 2 ports with known true calibrations, it looks quite identical. If you need something more accurate than that, you might want to really use the top wrench to make it more accurate. Right, so the last thing I want to show you is the QSOLT. So let's go to cal, mechanical cal, and change the cal type. And QSOLT. There's one step that's different. So we only need to count on port 1 using the ecal, and then we're going to connect directly port 1 and port 2 without the ecal connected to port 2. So let's go start calibration. So connecting port 1 to ecal, and I will leave port 2 hanging. Measure, and the next step is connect port 1 to port 2 directly. Finish. So as you can see that loss is about 0.03 and it's about 0 phase with the direct connections. So I'm going to put back. So as you can see, it looks quite identical to the previous reading, which is minus 20.0-ish dB, and the phase is actually on top of each other, minus 102. So there you go. It has shown you normalizations and 3 different type of ecal method to get almost same reading. So hope this helped. Thanks for watching.